Okay, like I said, we have to make a little change today because, as many of you know, there is a slight problem with our speaker today, so I'm going to be taking over. And what I'm going to show you here, this is actually meant to be a general presentation that I put together on my research. And a little bit of background about what I'm going to be talking about is what I call numerical cosmology. And so it's a combination of numerical relativity, which I went to graduate school for, and cosmology, which, as you know, is the study of the universe. So some of this talk is designed to be what I call a general audience talk. It's meant to start off very basic. So if at the very beginning, if you can't follow that part, then there's not much I can do for you here. But as we go on, it'll get more technical, and towards the end will be more for people who are doing research in the field. Also, another thing is, I must admit, I just gave this talk at University of South Florida in last fall, and so I haven't really updated it since. So there might be a few things that could be a little bit better in here. So I can start off at the beginning. And so this picture is meant to mean the very beginning. And so this is sometime around 10,000 years ago, and the first man is looking up at the stars and kind of asking himself a big, very simple question. Where the heck did all that stuff come from? And so this is the whole idea of cosmology, is we want to know, when you look up at the sky, where did all this stuff come from, and where did this planet we're on come from? And so the way cosmology works in the theories is that the way you study this is you build observatories. And they could start off with just a bunch of people looking up at the sky at the same place and comparing observations. Or they could be something more sophisticated like this. Like, this is one of the world's oldest calendars. It was originally built because when the sun sets during the summer or winter solstice, it shines, which are the longest days of the year, or longest and shortest days of the year. It shines right through Stonehenge at a certain angle. And by looking at this and observing it every day, you can tell how far off the solstices are, and you can tell from that what time of year it is. And you can tell with a lot of precision enough to plant crops. Because it might seem warm outside one day and then cold the next. And if you don't have a calendar, you can't really tell. For example, in Missouri right now, there's snow on the ground. Okay. Who would know it's spring? So, over time, observatories got more sophisticated. You've got the smaller telescopes like Galileo used. And then they got bigger. And then, to get more accurate, started putting them into space. There was a change in the speaker. So we started putting observatories in space, and then, and that's when we really got more advanced. And now, observations are one thing, but if you really want to get something useful out of science, you have to actually put everything together. And this is the best graphic I can think of for that. And when you put things together, there's always confusion about how things fit together and what stuff actually means. So this is, you see from the little cartoon, the first guy, Kepler, says, so you see, the orbit of a planet is elliptical. First guy says, what's an orbit? Next guy says, what's a planet? Third guy says, what's elliptical? So the whole idea now is to just kind of break this down and see what happened. Now, at the beginning, what we've done really is we start off right up here, where humans observe the cosmos. And everything we know about the universe comes from looking at these observations. And if we look out through observations, we can see all the way back to here. I mean, this is with our best telescopes and going into space and everything. Anything that happened before that, the universe was opaque, so light could not travel very far without being scattered. So anything before that, a telescope is really useless. And you actually have to use fundamental physics to calculate what must have happened. And what we get from that is the universe seems to be expanding as we look out. So that meant if you look in the past, it must have been smaller. And if you get smaller, you get hotter. And at this point, everything was so dense and hot that you couldn't see through it. And then you get all the way down here to the era of nucleosynthesis and the particle era and the electroweak area and the whatever the heck we don't know what happened back here era. And so this is where physics as we know it breaks down completely. So our physics is able to tell us what happened from here all the way up to the modern day, but not before that. And so because of this, this is where we have a lot of questions that come up in fundamental science. And so what we know is that as you go back in time, you get to this era called inflation, where the universe grew up really, really fast in a very short amount of time. And when that happened, we know that there were these things called quantum fluctuations, ripples in the space-time. And they fell in three flavors. There were scalar perturbations, tensor perturbations, or gravitational waves, and then there were vector perturbations, which are like electromagnetic waves. And what's happened since then is that, we developed our theories based on what happened back then and everything moving forward. And so a lot of what we know about how we got structures and all that stuff in the universe came from these initial perturbations. And so this is just talking about gravitational waves and what are they. Because you can imagine a scalar perturbation basically means you just take something and you create little inhomogeneities. And a vector perturbation, you just imagine a lot of light. But what is a tensor perturbation of gravitational waves? And so what that is that, according to Einstein's theory of relativity, if you take space-time, and you think of space-time as like a sheet, a rubber sheet, and you put a bowling ball, then it'll actually cause that sheet to curve. And that curvature of the sheet is what we see as gravity. So gravity is actually an effect of warping space-time. It's not a particle, it's not really a force in a conventional sense. And so what happens in Einstein's theory is that space-time is going to tell matter how to move. And as you move into this curved space-time, you'll feel an effect like gravity. Just like you would see if you put a smaller ball near this curved sheet, it would kind of roll in. And matter tells space-time how to curve. So anytime you have something massive, it makes the space-time curve. And so what happened in your early universe, if you have all these ripples in the space-time that come out of this initial inflation of the universe after the Big Bang, then all the matter that's there should have been affected by this curvature. And so this is what gravitational waves look like. If you can imagine you have a ring of particles and a gravitational wave passes by, what it'll do is it'll cause the ring to become an ellipse. First in one direction and then the other. And this is just a gravitational wave just kind of moving these particles apart, pushing together. And so literally, as these gravitational waves pass by, it's like we're all getting a little bit taller and shorter and fatter and so forth at the same time. The difference is that these changes are very, very small because the gravitational waves are small. And so this is how we would actually detect a gravitational wave, is to actually have an interferometer set up where what this interferometer does is it measures the distance change along the two arms. And so if one arm gets a little bit longer and the other one gets a little bit shorter, then you can detect that by a gravitational wave. The trick is, though, is you have to be able to remove every other potential source of noise. So it's just not a random thing like a laser shot noise or thermal noise or seismic noise or anything like that can interfere with it. Even worse than that is that the change in length, delta L over L, is on the order of 10 to the minus 21 for most of the sources of gravitational waves that we know of. I mean, and they get weaker from there. So if you're talking about detecting a change of 1/10 of a millimeter, which should be pretty easy. 1/10 of a millimeter is pretty measurable. It would require these arms to be 3 light years long. And that's just not going to happen, obviously. And if you can make 4,000 kilometer long arms, which are still pretty big, the change you get is only about 10 to the minus 13th, which is about the diameter of an atomic nucleus. Imagine a hydrogen atom and just the size of the proton. And so if you could make 4 kilometer long arms, which are still really big, but doable, that requires something, then what you end up with is 1,000th the diameter of an atomic nucleus, as far as your size. So we can detect these on the ground, or we can do this in space. And this is NASA's version of this gravity wave interferometer. And it has some advantages to it. One is that you can make the arms longer because you don't have to build a vacuum or a structure between them or anything like that. And you're free from seismic noise, so you can detect lower frequencies. Lower frequency gravitational waves are higher amplitude. So you can, so because they're higher amplitude, you're looking for a stronger signal, but you're also got longer arm lengths, so that the signal is actually going to be bigger anyway, or easier to detect. So these arms are 5 million kilometers, effectively. So it makes it work a little bit better, but you're still detecting a small signal, and you're looking at a lower frequency. And so the way these work is there's several interferometers set up all over the Earth. This LISA mission is, they've been trying to launch it sometime in the next decade. And we'll see what happens with NASA funding. And so what happens then is that if you can actually have the sensitivity to detect and actually launch these detectors, then this is the spectrum of gravitational waves that we expect to see from the early universe. And this was actually calculated by one of our students here. And so what he did was he looked at perturbations from the early universe according to a guy named Gr when he was calculating out what the spectrum of these were. And he looked at it in terms of regular and then a modified spectrum caused by birefringent gravitational waves, which we'll go into. And you can see that this is the LISA sensitivity band. And this is where the gravitational waves would fall into the spectrum, so it should be able to detect this. And this is LIGO, which is the ground-based detector, their sensitivity band. And actually there's another way that's been worked out. It's fairly recent. It's called another technique for detecting these gravitational waves called pulsar timing, where they actually use pulsars as these regular clocks. And with the idea that if a gravitational wave were to pass between us and the pulsar, it would either lengthen or shorten the distance of the pulsar, which would actually delay the signal getting to us. And then by using that, we can detect gravitational waves in an ultra low frequency, like in the nanohertz range. And that could be done with radio telescopes as opposed to using this special equipment. And so that's another thing that's been thought of, but hasn't really been implemented yet. So the difference here, just knowing a few things different between gravitational and electromagnetic radiation, and you can see the whole column here, but the things I want to point out are that, first off, the electromagnetic waves are oscillations that go through space-time, and gravitational radiation are oscillations in the space-time itself. And then also there's a difference in the frequency range where electromagnetic waves tend to be higher frequency. Gravitational waves tend to be like about the order of sound in frequency. So they start about 1 kilohertz and go down. And then also the most important thing is that electromagnetic waves are easily absorbed or scattered, and gravitational waves can never be scattered or significantly. The only thing that can block a gravitational wave is actually a black hole. So if you actually have a signal that came off from the early universe and it's been traveling since the beginning of the universe for the gravitational wave, you can still detect it as if it's never been absorbed or scattered or affected or anything. But with an electromagnetic wave, you've got that limit. You can only see back about 50,000 to about 500,000 years after the beginning. So because of this, if you can detect these gravitational waves, you can do a lot of interesting things, including interesting things in cosmology. So here's the big question. Why should anybody care about gravitational waves? What's the big point? So as you can see here, gravitational waves can excite turbulent modes of oscillation in the plasma, kind of like a crystal is excited by sound waves. And if you excite different modes, then really early on in the universe, when the universe was really small and not really doing much, you would expect that that would actually cause something to happen, something significant. And the question is, can these excited modes contribute to the formation of structures in the early universe? Now, the reason why I bring this up is because of plasma turbulence or plasma physics. If you look at a lot of the literature on early universe and structure formation, there isn't much mention of gravitational waves. And there are several reasons why, and this is one of the things that's not included in the slides. One reason is because early on when they were developing all these structure formation things, most of the authors did not look at gravitational waves because they made an early approximation that there were no magnetic fields in the early universe. They just kind of assumed that was true. There was no proof that there weren't any magnetic fields back then, and there was no proof that there wasn't any. So it's kind of like one of these things where later on, as cosmology got more advanced and we got more sophisticated, people started asking the question, well, we have these huge magnetic fields in galaxies and superclusters of galaxies. Where did they come from? And some of the theories said, well, they must have been early at the beginning. Well, if you ignore magnetic fields, then what happens is that the plasma, which we know occupied the early universe, looks just like a hydrodynamic fluid, like water. And if you model the effect of a gravitational wave on water, the lasting effect is nothing. However, if you model the effect of a gravitational wave on a plasma, what we're going to see is it's going to be a lot different than that. So there's a significant difference just based on that simple assumption of whether or not there were magnetic fields. Because if there were magnetic fields, then you need to model it as a plasma. If there weren't, you could model it as this hydrodynamic fluid. And it's sort of like if you're trying to model the sun. If you're trying to develop a simple model of the sun, you actually want to predict the weather on the sun. Would you model it as if it weren't a plasma, if it was just a ball of water? And if you did that, could you get anything accurate out of it? So, I would say no. And there's obvious reasons why. And so a lot of this stuff with the plasma turbulence is actually credited to John Shevlin, who has been working with the physics department here for several years. And you can see here, a plasma, basic definition, is just an ionized gas of charged particles or magnetofluid. And they call it this because they have magnetic fields are affecting the fluid. A plasma kinetic theory is basically where you have a probability density function where you're describing the action of a bunch of ions and electrons in the fluid. And magnetohydrodynamics is basically where you are looking at the dynamics of the fluid, and he has here velocity, pressure, and magnetic field as all properties of this fluid, but you can also add density onto this as well. And so if you make this turbulent, what that means is that the mean value of all these magnetohydrodynamic variables are random. And so there's not necessarily any direct pattern to it. And the external magnetic fields and rotation are going to affect the plasma dynamics. So if you look at a plasma and it's undergoing some kind of turbulence, then you can see if you look at this little section of plasma, every section of it, like a box, looks like every other section. So you can model this with periodic boundary conditions, and you can approximate all of the things going on anywhere in the fluid by any other part. And so the way he does it then is he looks at the Fourier components, looking at this in terms of frequencies as opposed to points in space. It's a little bit differently than what I'm doing. And so this is called a spectral method, where you're actually calculating these using what's happening within the spectrum. And then he took us a little step further, and he developed the evolution equations for how do these variables change with respect to time within this plasma undergoing turbulence. And these are nonlinear terms that snuck in. And I'm just skipping towards some of the conclusions, which are that if you're dealing with just a gas, like let's say you're a hydrodynamic fluid or something where there's no magnetic field in the early universe, what happens is that there is one invariant that you use to describe the statistical mechanics of the gas, and that's energy. But if you're dealing with an MHD fluid, and this is ideal MHD, but it also works for a real MHD fluid where there is viscosity, then all of a sudden there are three invariants. This is energy, cross-helicity, and magnetic helicity are the three, where these two are pseudoscalars. And what happens then is that if you look at all the different cases where you have whether or not you have a mean field or a mean velocity in this magnetofluid determines how many invariants you get. So this is having a zero mean field and a zero angular velocity. You have three invariants. If you have a non-zero mean field but a zero angular velocity, you have two invariants. Same thing if you have a zero mean field and non-zero angular velocity, you have two invariants. And then depending on how the two relate to each other, you have this parallel helicity, which is actually like another invariant. So what's happening now is that you've got a lot more sophisticated dynamics from a plasma than you would get from just a regular hydrodynamic fluid. And so this is the whole point, because now these are the three invariants that you have: energy, cross-helicity, and magnetic helicity. And these are the statistical mechanics, or the probability density functions you get from each of them. And what happens, and he's gone through a little bit of this, where he actually tries to calculate the eigenvalues that result, or what you would expect to happen. But what happens is that if you were to plot the phase portraits, where you're actually looking at the different components of each of the different coefficients, like the velocity and the magnetic field and the pressure throughout the fluid, then what you expect to find in most fluids is that if you make this thing turbulent, and it's homogeneous turbulence, that the mean is going to fall around zero. Zero for the imaginary part, zero for the real part. What happens in reality is that because it's a turbulent plasma, you actually see the mean up here. This is 0, 0. This is the actual mean. And you can see in each one of these cases, you've got non-zero mean values for these things. What that implies is that we have non-ergodicity, or broken ergodicity, which means that time averages are not the same as ensemble averages. And you have this homogeneous turbulence, and this is really the beginning of coherent structures. So if you take basically what this is saying is if you take a plasma and you shake it up and you make it, and it's undergoing turbulence. You can imagine like you take a fluid and you mix it with a spoon, and you see after a while it forms that little vorticity in the middle of it, and then and then you stop stirring it, and eventually that vorticity goes away. In a plasma, that's not the case. In a plasma, you stir it up, and you get that little vorticity thing going, and it stays there. So this is why I think it is that you can't model the early universe as a fluid. You have to use this whole magnetofluid thing, because a lot of the dynamics you're getting from these gravitational waves interacting with the plasma, instead of them just dissipating, they're going to stay there. So this is the basic idea. So the goal of what I've been trying to do is we're going to apply the physics and mathematics of MHD turbulence to gravitational waves and relativistic plasmas. And the idea is that if you have a gravitational wave, since it causes the space-time to expand and contract, if that passes through a plasma, it'll cause the plasma to expand and contract. And when it does that, it can actually cause the plasma to become turbulent. And it can actually cause a lot of this dynamics. And it's mostly because the electromagnetic field's interacting and things like that. And so we want to demonstrate that you can form coherent structures, and these are cosmic magnetic fields, density and temperature variations, and relic gravitational waves as a result of the interactions of gravitational waves. And to do this, and this is the hard part, we have to actually build a computer code that integrates both the dynamics of general relativity in a curved space-time with the dynamics of the plasma field. And the two of them are going to interact. The gravitational waves and the plasma are going to kind of move back and forth, possibly exchanging energy back and forth between the two. And so what we did is we wanted to simulate the early universe after the inflation event, and where we know the universe was just made out of this homogeneous plasma, and it was a gravitational wave field. And you could do the classical physics. You don't need to use quantum physics or anything, no exotic physics. Everything here is based on physics that we know and understand and has been around for a long time. And we started at t equals 3 minutes. Just to let you guys know, the reason why we started at t equals 3 minutes is because that was the earliest we could start the simulation and get it to work. It has nothing to do with that being the perfect time to do it. But at this t equals 3 minutes does correspond to that era of nucleosynthesis when you're first starting to get atoms, or not atoms, but at least ions and heavy particles forming, and the nuclei of atoms. So what we're trying to do from here on out is improve this and actually go much earlier and evolve much longer. And I'll go into that a little bit at the end. So this is the space-time metric, and this describes how the space-time is curved, where this beta term corresponds to shift, and this alpha is the lapse, if you're calculating from one space-time element to the next. And this is called the extrinsic curvature, which describes how the space-time changes with time. So if you know how something looks at a particular time, and you know how it changes in time, you can evolve it forward in time. And then these are the other variables, basically just rewriting this stuff in a more stable way, so your code doesn't blow up. And then these are the variables that go into the plasma field. We've got this mass density, the momentum density, the energy density, the magnetic field, the velocity of each particle, and the pressure. And so just like any other fluid. And so the way that these are tied together is with the Einstein's equation, which this is the kind of long way of writing it out. And basically what happens here on the left-hand side, this is the curvature part. So this is the curvature of space-time. And on the right-hand side, this is the stress-energy tensor, which describes the plasma field. And so a change over here affects a change here and vice versa. So effectively, you've got a realistic model of the space-time and the fluid on the space-time. Both of them can interact. The stress-energy tensor is made up of this stuff. And these are the fundamental variables of velocity and the magnetic field and the curvature of the space-time and the pressure and the densities over here. And H, in this case, is the enthalpy, which is the same thing you get in statistical mechanics. And then you have these other terms involving the magnetic field here. And so what we did when we built the model is we have an observer that's co-moving with the fluid. So you set the lapse equal to 1, which is how you're evolving forward in time, and the shift equal to 0, and you're assuming that the forward velocity of the observer is just somebody that's standing still and watching the universe evolve. And so you're starting off at t equals 3 minutes. The plasma is at a temperature of 1 billion degrees, and it's mostly made up of electrons, protons, neutrons, neutrinos, and photons. Has an energy mass density of about 10 to the 4th kilograms per meter cubed. And the universe is radiation dominated, and we've also been able to calculate the Hubble parameter, which is the expansion rate of the universe at this time. And so if the age of the universe is 13.7 billion years, you can use this in the current measurements of the cosmic microwave background radiation to calculate the scale factor of the universe at any point in time. So for t equals 3 minutes, the universe was about 1 billion times smaller than it is now, and 1 billion times hotter by coincidence. And so the specific internal energy, which is another one of these terms that we got here, is calculated from the temperature. The pressure is calculated from using the gamma law of pressure, and this relates to density. The electric field is set to 0 because the observer is co-moving with the fluid. So he doesn't see any electric field, but he will see magnetic fields. And a magnetic field is set to 10 to the minus 9 Gauss, which may seem small, but what this is this is the based on some research of what the magnetic fields in the early universe must have been like at this time, and based on our observations of the cosmic microwave background radiation, we can say that this must have been the highest possible magnetic field at that time. And so what this does with this simulation is that if we can run the simulation and do it accurately enough, then it'll allow us to actually put better limits on what the magnetic fields in the early universe were. I mean, it could be that we put this number in and we see that structure should have formed a lot sooner, or should have been much more densely packed, in which case this number is too high and we can adjust that. But also what this does for us is that it's going to allow us eventually to run a simulation where we're using not just these gravitational waves, but also scalar perturbations in the early universe and dark matter, and putting constraints on how much dark matter there must have been to help form the universe, or how strong the scalar perturbations were. And we can do all this by just running a simulation and then extrapolating the results forward and comparing it to the cosmic microwave background radiation observations. So this is the space-time that we start off with initially. This is the perturbed Robertson-Walker metric. And you can see here, this is the scale factor, which is how big the universe was. This is time, where this is actually called conformal time of the universe, not cosmic time, which we usually count in. This is the perturbations coming from gravitational waves, and then this is the metric terms. Then we've got the spectrum of the perturbations, which is given by this equation, which comes from Grishchuk. And we can modify the spectrum of perturbations through, like this is the birefringence, which comes in as effects from string theory or quantum gravity. So we can incorporate other theories into this just to see what happens. And basically what you get is an engine for calculating what the spectrum, how much perturbations are in the universe and how structures form. And so this was just the preliminary results of doing this with the early code using finite differencing and starting at t equals 3 minutes. And what happened is, at this point, t equals 0, everything was flat. The universe wasn't perturbed. When you turn on the gravitational waves, what happened was the density, this is the maximum density of the fluid. This is the minimum density of the fluid. And so you could see that there became parts of it that were on the order of 10 to the minus 10. And that's basically like saying, you know, the entire density of the universe is on the order of like 3,300, or about 3,300 kilograms per meter cubed. This is about 3 times 10 to the minus 10 kilograms per meter cubed. So it's a very tiny variation, but it's there, and it persists after a while. So what this is saying is that just turning on this gravitational wave made these perturbations appear in the early universe from gravitational waves without adding in scalar perturbations or dark matter or anything like that. And then you can see this is the total variation between the peak to trough, crest to peak, trough to peak variation that you have here, which is on an order of 6 times 10 to the minus 10. So it's about a part in a trillion in variation. But it's non-zero. And the thing is, this ran for a total of from t equals 3 minutes to t equals 5 minutes. So for 2 minutes of the early universe with just gravitational waves, you got this much variation. If you allow this to happen over long enough time, where you actually get the effects of gravitational collapse and other things, then with enough time, adding in several 100,000 years after this, that's when you can actually get to the point where you might actually have observable structure. And so this is just a little bit about what we need to do in order to make better results and actually do more science with this. And the first thing is rewriting the Gr Mhd code. I said in terms of spectral, in K-space, but really what we mean is in terms of spectral methods. Because the drawback to this is that, when you're doing the simulation, you're doing it very, very early in the universe, where the universe is really, really hot and really, really small and dense. You're trying to expand it out. You're trying to expand over cosmological scales. We have this huge variation between data points. Then what happens is the code can't handle that, and it crashes if you use finite difference. So we're working on doing that in spectral methods, and that's actually what Andrew's working on. He's going to be talking about that. Adding viscosity into the equations, and that's actually just to make them more realistic to what the early universe was like. And we've already looked at how to do that. One problem is nobody really knows how much viscosity there was that early in the universe. And so that's another challenge. Adding in metric perturbations, scalar metric perturbations, and I could also add to this dark matter. And the reason why is because we want to be able to model the universe as accurately as possible given what we know now. I mean, the current simulations that people have, they ignore the magnetic fields in the early universe, and they ignore the gravitational waves, and they only put in the scalar metric perturbations and the dark matter. And so once we add this in there, the idea is that you can start off with your universe with your initial conditions you want, with the gravitational waves and the scalar perturbations. And then you can add in however much dark matter there should have been at that time. You can add in how much magnetic fields there should have been at that time. Let the thing evolve, and then extrapolate the data up to the cosmic microwave background radiation and just see how it compares. And then you can, play with the recipe until you get the right ingredients. And once you've got the right ingredients, it tells us a lot about the universe that we don't know already. And that's about it. So, like I said, it's the whole idea of this is to just look at how do we build a universe, and how do we do it numerically. And that's why I came with the name Numerical Cosmology. And and do something that's accurate. All right, so any questions? Yes?
How fast does a gravitational wave travel?
Oh, that's a good question. It actually travels at the speed of light, we think. Nobody is 100% sure because we've never observed one before. So, but the idea is that if the gravitational wave, let's assume we're particle physicists for a second. If we assume that they're carried by a particle, and that particle is massless, then all massless particles should travel at the speed of light.
Is that the graviton?
Yeah, the graviton. If you assume that the graviton is actually a massive particle, then it won't travel at the speed of light, it'd be a slower speed. But if it's a massive particle, then it also gravitates, and you have enough of them that will stick together. And that would be something else that would be interesting to figure out. But one thing is that you can actually use these gravitational wave interferometers to detect, like if you had a source that emitted both electromagnetic and gravitational radiation. An example of that is a supernova explosion, where it blows up, so there's a lot of stuff moving really fast, so there's a big spike in gravitational wave, and there's also a spike in electromagnetic radiation. Then you can actually look at the two and detect them both at the same time, and see if you detect one before the other, then does a gravitational wave travel slower than the speed of light. And there's a few other tricks involved in that too. Yeah?
Gravity is the unique force or particle graviton paired with all the others. Is it possible, and I've read something where they think that gravity didn't exist for the first part of the universe. It came into being when all the matter and atoms formed to a certain extent. It produced the gravity. It's just a mention. I don't know if you've seen that.
Well, let's just put it like this. I want to go back to the slide that we have. If you look at this, okay, basically we got this error down here, the Planck error, and we have no idea what happened down there. So it may be possible that there was not a gravity back then, or there wasn't any other any of the forces of nature that we know of as we see them today, and that it wasn't possible until we got up to that point. But we do know that gravity does seem to exist down here somewhere. It's just in this grand unification. This GUT is grand unification theory era. And that's where the four forces of nature were all kind of combined into one super force, and there was no distinction between them. So, yeah, it's possible that, I mean, at least up here we know that there was something called gravity. Because at the rate the universe was expanding and everything else, it all fell into place and followed this Robinson-Walker metric. And so what I'm talking about is maybe starting our simulation like somewhere up here. So there's a lot of physics down here that we're still not quite sure about. And this is actually like frontline theoretical physics stuff that Stephen Hawking is always talking about, type of thing at that point. And we really don't know. Because like I said, if you take the laws of general relativity literally, and you take the laws of quantum mechanics literally, they work fine up here. They're completely separate. You don't use general relativity to solve a quantum problem. You don't use quantum mechanics to solve a general relativity problem. And except inside a black hole, things work pretty well. But when you get down here, if you take them both literally, then it tells you that the Earth doesn't exist. I mean, the universe doesn't exist because they just don't work. So, could be. Yeah.
I was doing my paper for the Research Arts Conference on visualization, and John Hawley's model for black holes actually had the picture of the black hole coming out of the model. I was wondering if your model could be something that relates to the cosmic background radiation and showing a visual representation of that. And then I was wondering for publishing, when you publish an extrapolation of an existing theory, because you're adding like gravitational waves to the existing published, how do you do that? Do you publish an extension by adding it, or do you usually publish saying you're proposing something new and you leave out the old stuff? The third thing, what language are you using?
All right, that's like three questions, right?
Yes, sir.
Okay. All right. Well, first off, the visualization.
Yes.
One thing you're doing if you're running a simulation like this, you always have to use visualization and the reason why is that there's so many particles and there's so many things going on that really all the models look alike after a while. If you're just looking at numbers on a computer screen. And so what you do is you have to be creative in how to visualize it. Like, one thing is like we had one simulation where we're running it using OpenDX. And when you see the animation starting off at the beginning and you're just looking at density, and you see little spots occur, and these spots will kind of stay there and move around, or you're just looking at a one-dimensional plot and it'll stay there, then you can get a better idea of what's actually going on. Because I looked at this early on testing the code. I had a problem where I had an analytic solution and had a numerical solution, just trying to see if if the effect of the gravitational waves on the plasma was what it was supposed to be. And I was just looking at the raw data and I couldn't figure heads or tails what was going on. I just knew they weren't the same. When I visualized it, I was able to see, aha, I'm getting twice the answer I'm supposed to. Especially when I increased resolution, it got sharper and sharper. It was in phase. It was twice the number. And that was when I realized I had a factor of 2 early on in the equations that threw everything off. but it's basically just easy to track down problems when you do the visualization. So it's not just for presentations, it's also just to understand what's going on. And when you're doing a simulation like this where you're evolving it in time, you can actually create movies of it. And you can actually create like an entire movie of the universe starting off as this homogeneous thing, and then structure just kind of evolving over time, and spots getting more and more dense and spreading out, and the universe expanding and all that stuff. As far as, what was your second question?
It was about publishing. How do you publish an extension? Do you publish an extension, or do you publish just focused on the piece you're adding? How do people normally publish?
You mostly focus on, well, the way you write the paper with something like this. Recently, I have a paper to submit that's being reviewed on this stuff right now. And the first part is the introduction. And in the introduction, what you're doing is you're summing up what's been done before, but you're doing it from your point of view. So in other words, there is like the kind of the standard party line that you would have in something like this, where people would go through and they'd say, this is what we know about cosmology, and they wouldn't even mention gravitational waves. What I do in my introduction there is I would talk about that, but I would focus on why they're not mentioning it, instead of saying, instead of just literally just reiterating what they're doing. And I'm focusing more on what I'm doing that's original. So, in my paper, I focused a lot on the magnetic fields being left out, and kind of, I reiterated some of the literature that was already out there about the perturbations in the early universe and how it included gravitational waves. And I reiterated some of the stuff that they had where people early on concluded gravitational waves didn't do anything. But then I also made a very strong point that the reason why they said they didn't do anything was because they weren't looking at a plasma. They were looking at a hydrodynamic fluid. And that the physics is right, but they got the wrong model. And so I made a point of just, stressing that this is the model that you need. And that, we're in the computer era now. We can't just ignore things that we ignored just to make our calculation easier. We have to do with something accurate. And so I made a point there. And finally, as far as what this is written in, I use a framework called Cactus. And Cactus is an open source framework. It's actually, the code itself is written in a combination of C and Fortran, or C, C++, Fortran 77, and Fortran 90. And so it's a mix of a lot of different things. And what Cactus does is it allows us to just kind of write these little thorns, where each thorn handles a different part of the code. Like one piece of the thorn actually writes the output so that we can put into the data visualization program. Another thorn will actually do the simulation of the plasma. Another thorn will do the simulation of the space-time. Another thorn will do handle errors. If they get too big, it'll shut things down. Another thorn will set up the basic computational grid. And so basically I just have to get all these thorns to work together. And that's the way my code works. So really, since I didn't have to write the entire Cactus framework from scratch, which would be, thousands, possibly even millions of lines of code, I just focused on, utilizing the ones that already did what I wanted to do, and then added in the ones that I needed to do other things with.
Thank you.
Yeah.
How do the gravitational waves travel? I mean, is it planar, and are they only in one direction? Do they amplify each other if they cross paths?
Yeah, that's a good question. In the early universe, these gravitational waves actually travel in all directions. Like if you're talking about gravitational waves from the early universe, and they would be moving in every direction, and they would actually be like standing waves as opposed to traveling waves. If you're talking about gravitational waves from a source like colliding black holes, then for the most part they'll be traveling mostly in like a plane, but but they'll, as you move out, they kind of there'll be more in one direction than other directions, you know. But for these from the early universe, we expect them to be coming in from all different directions and forming standing waves, but they'll be at different phases. And you know, so it's really it's not like there's a source to it. And they'll also have different polarizations too. Like they have the plus polarization, the cross polarization, and kind of like we talked about the birefringent ones. With those, that was a combination of the plus polarization, where it was, you know, let's see if I can get to it. This is the plus polarization, and this is the cross polarization. You can see it forms like an X. If you combine the two of them together, then you can imagine you have this ellipse, and it just kind of rotates around. And so that's, and it can rotate to the right or to the left. So it's the same thing as like with light, where you have, you can be polarized in this direction or that direction, or you can have a rotating polarization.
Cross, do they amplify?
Yeah, if they cross, if you put two of them together, then they actually would amplify. It's actually possible that you could have two gravitational waves. They could come together in empty space, and they'll curve space so much when they cross that they'll form a singularity, which is like a black hole. And you can actually form this thing without any matter interacting. So it's really interesting dynamics to it. It's just, like I said, it's this stuff hasn't been studied a lot.
Singularity naked?
I think it would be. I think you could form a naked singularity like that. Because actually, no. I think you might still have a horizon around it, but I'm not sure completely. Yeah.
Well, you mentioned, I think, that you use classical physics in your calculations now.
By classical, I meant non-quantum.
Yeah. Why is that? I mean, somewhere down the line, they have to join together. And there's a non-locality factor here, which could be in relativity and certainly in quantum mechanics. Where do we get, I mean, you say at the top of the picture, you got both are separated and they're existing, but what about the bottom? There's nothing there?
Well, it's not that nothing's there, it's just that we don't know it's there. So the reason why we stick with classical physics is because we understand it. And that's why we don't put in quantum gravity and things like that and get to that point where you can't really, like what happens in that picture is, let's see, I think it was this one, is that when you get down here at the bottom, you literally reach a point where you can't talk about gravity in terms of general relativity like Einstein did. You would literally have to take into effect quantum gravity, which could be like string theory or loop quantum gravity or some other theory, which really may be wrong, put it that way. I mean, like general relativity, we're pretty comfortable with it. It's been well tested out, and we know that at least at that scale it works. And with, if we talk about doing plasma physics at that scale, we know that pretty comfortably that those equations are right. But if you start bringing in quantum gravity at that point, then you may not be right because it's never really been tested. And so we're trying to avoid using too much stuff that's been untested. Because, I mean, also another thing, and this is a challenge whenever you're doing computational physics, is that what we're really doing in computational physics is we're evolving equations. And we're solving equations that you can never solve by hand. So how do you know you got the right answer if only the computer can tell you that's the right answer? And nobody else, there's not like a textbook out there. There's not like somebody who's going to sit there with a Mathematica program on their desk and say this is the right answer. It's like you're the only person that's ever solved this problem. How do you know it's right? And so if you're doing all this other stuff and it's difficult enough, and like a little error can creep into your equation and throw it off, and your right answer is a wrong answer. But if you're really throwing in new physics that you really, hasn't been established, then the chances of you being wrong are much higher. Yeah.
Along those lines, I'm still trying to understand how the method you used to reproduce results in a model, and Because in one of the other classes, what
Yeah.
they said was, you take a document that's already been published, and they present their method, and from that, you should be able to take their method and reproduce their result in a model if they give you the right information. And then, so I was wondering, did you take an existing model that was published and start from that point and verify their results? Or did you, and how are you going to publish the method? Are you just going to publish the equations?
No. Well,
Are you
one
gonna
thing
actually
is,
publish the cactus
yeah.
code?
Well, one thing is, no, you can't publish the code. First off, one reason why is because, basically you publish the code, and then anybody who has the code can just basically they can write all the papers, and they don't need you. So that's just never really a safe thing. What we actually do know in the method is these equations. And so this is really the reproducibility part of it. And it's saying anybody out there who can write a code that involves these equations, and they can start off with the initial conditions that we have. If they do that, they'll get the same results. And so when you write a paper, you welcome them to do that, but you're not going to give them the code to do it.
How about did you actually reproduce somebody else's?
Yeah.
Before you got?
Yeah, actually what happened was in one of the papers written by a group at University of Illinois, what they did was they actually wrote a Gr Mhd code. And it was, by the way, nobody had even written a code like this until about 6 years ago, if that. And so what they did was they wrote this Gr Mhd code where it actually had general relativity and plasma physics all combined together. And one of the tests that they did of their code, they had several tests in there to where they proved that their code works. And one test was they actually worked out by hand what happens when a gravitational wave hits a plasma field. And it causes the plasma field to oscillate without certain alpine and magnetosonic modes. And they were able to publish semi-analytic results of that, and basically saying that if you run your simulation for a short amount of time before the collapse of gravity and before these other things all take effect, then these are the results you should get. And so what we did was we used these semi-analytic equations and we compared them to the results of our code running, where we had a gravitational wave and ran into a plasma field and made the simulation work. And what we got was the same thing.
Huh.
And so that showed, at least showed that when we're generating gravitational waves, or generating plasma waves from the gravitational waves, that we're actually doing the right thing. And that was one of the things that needs to be included in the paper, because it's kind of like saying, we have this complicated code, how do you know it works? And this is just kind of our explanation for how we know it works. There were other tests that they did as well, like they did shock tests, and they did other tests involving like a black hole, but that really weren't necessary for this code, since what a shock test, that means is they actually had supersonic waves or collapses that were taking place. They were sending shocks through the fluid, and they were modeling what happened and comparing it to analytic results. Well, we don't have any supersonic waves in here, so no point. And we didn't have any mass like a black hole or anything, so we didn't do any tests with that. So we just picked the appropriate tests and did them, verified that everything worked. And once we verified that everything worked, that's when we moved on to actually trying to do some physics.
You mentioned that you like to visualize your models. Is that a dangerous thing sometimes? Because mathematics can lead you another way.
Yeah. You can. Well, it's a good thing, but sometimes the data visualization for something like this can be a lot of work too. So it's kind of a balance between how much time you put into visualization and how much time you spend on the model. Like sometimes, like the one I use the most often is a program called Y-Graph. And the reason why is because it's just a simple 2-column calculation where it literally takes it takes each element and it just plots it. Like, what happens to this quantity versus its position in the x direction, and then it plots it versus time, so you can actually see your wave evolving. But it's only just one-dimensional. And it's enough to where, I can look at this and I can see whether or not the analytic solution is matching up with the numerical solution, the analytic are matching up. But, sometimes you see all this thing and they're just a bunch of dots. One thing this data visualization can do is it can allow you to look at things like take a Fourier transform of the whole thing and look at the spectrum and see if the spectrum lines up. And there's just a lot of things like that you need just to see if you're on track. But if the mathematics isn't there, it'll show up very quickly in the visualization, because it won't even, most of this stuff, if it's done right, it'll look somewhat right. Like an example here is when I gave my final graph here, preliminary results. See, this isn't exactly smooth, but it does illustrate what's supposed to be going on. So it's not the prettiest picture to look at, but it does mean that, this is what's happening. But if you want to get more in depth into what's happening here, like we see that the maximum, what I'm plotting here is this is the most dense part of the entire fluid, and this is the least dense part of the entire fluid, and it normalized around 0. And so what happens here is if I want more detail about what's going on here, like I could say, well, this is the most dense part of fluid, but it's rapidly changing. And then if I do further data visualization, what I've seen is that there's like a peak that forms in the fluid, and there's a big dip or trough that forms somewhere else. And they may move around a little bit in 3 dimensions, but they don't actually disappear, and they don't actually disappear in a new one form or anything like that. So these are like continuous lumps in the fluid. And and that's something you can only really learn from data visualization, because just looking at the numbers won't tell you.
That's showing fluid densities or plasma densities, just kind of round, traveling with the gravitational waves.
Well, actually, no, they don't even travel. Well, the gravitational waves are standing waves, so they're not even. But they're just basically, it's almost like everything was smooth on this table, and then all of a sudden, they're just after the gravitational waves start, a kind of a lump will form, and that lump might move around a little bit, maybe move around in a circle, or move around, but it doesn't quite disappear, and that's what we're seeing. You had a question?
No, I have two.
Okay.
Are there standing gravitational waves and moving gravitational waves?
No, just standing.
Just standing.
Mm-hmm. Well, the reason why is because if this is really a homogeneous space-time, then gravitational waves can't really be coming at you from a direction. They just have to just kind of oscillate up and down, and just standing at different frequencies. Yeah.
I guess that probably answers my second question, but I don't really know see the answer.
The way you can think about it is like if you have traveling waves coming in, and 2 traveling waves come in, and then they hit each other, they're going to form a standing wave. So it's like if just picture one coming from the left and the right, and things aren't homogeneous if you've got actual traveling waves.
Okay, the second question: if you have a spherical mass, and just kind of as a thought experiment that spherical mass is changing mass drastically, and the amount of mass in it is like oscillating.
Right.
It gets really great and then smaller and really great, small. Is it going to be emitting gravity waves, or is that just a case of changing gravity and it's too simplistic because gravity waves actually happen just in space?
No, it would actually emit gravitational waves. If you had a mass and it could actually change its mass. Like, let's suppose you have something, let's say the sun would disappear tomorrow, like that. Then all of a sudden, the sun right now is curving the space-time around it. If the sun were to disappear, then all that space-time would kind of snap back. And what would happen is that would cause kind of a ripple effect, because the whole space-time would go from being like this to being like this. And so that indentation in space-time would just travel outwards. Kind of like you turn on a light. When the light's off, there's one thing. You turn it on, there's a big light there. You turn it off, then there's kind of that last bit of light that kind of spreads out.
But then it would be traveling and not standing.
Yeah, that's if you had something like that. We're talking about the early universe here. Then all of a sudden, what happened with the early universe was you had all these quantum fluctuations everywhere in the universe. And they were homogeneous, they were everywhere. And then they just expanded, and they got bigger. And when they got bigger, that was what actually drove them into becoming gravitational waves. But they weren't coming from a single source. Like with the sun, that would be coming from a single source. So there's no one source. The whole idea is that anytime you have anything with any mass, and it moves or it changes, it's going to emit a gravitational wave because the curvature of the space-time is changing. But when everything in the entire universe changes all at once, then there's no single source. They're all over the place. And so if you can imagine, it's like there was not like a center of the universe that did this. It was like everything. Yes?
Is it correct to say then if that happened to our sun, it just disappeared, that we'd see it and feel it at the same time?
No, you take about 8 minutes and then you
Well,
all
at
die
the same
horribly.
time in an 8-minute interval.
Yeah. Well, pretty much. Basically, if the sun were to disappear, then, yeah, you're right. The gravitational wave would get to us at about the same time the last light from the sun would be getting to us. And then right after that, we'd all be dead and we wouldn't even notice. So we wouldn't even have time to analyze the data, but we wouldn't have any problems after that. All right, any other questions? Yes?
I get all these models all assume the energy.
Not really. Well, yes and no. The reason why energy is a conserved quantity and energy is constant is because in classical mechanics, time is considered to be homogeneous, which means you run things forward in time and backwards in time are the same thing. When you bring in cosmology, what happens if the future of the universe is different than the past because the universe is expanding in the future and it was smaller in the past. So therefore, the universe is really not homogeneous, and that whole energy conservation doesn't really mean the same thing. So when they say energy conservation in terms of like these little plasma dynamics or fluid dynamics, what they're talking about in just that little local area before you really take into account all this expansion and stuff, then in that sense it's constant. And then what happens is the laws of thermodynamics take over as you move things forward, and it becomes less dense, and so it cools off and things like that. So and that's one interesting thing here is that like you've got all this thermodynamics going on, you've got all this fluid dynamics, you've got all these magnetic fields. At the same time, the universe is getting bigger. And so nobody's really put all that together to see what happens. And that's a problem that you're not going to solve without a computer. Are there any other questions? Okay. That's it. Thank you.